皆さんおはようございます。東大情報基盤センター、JCHPC の中島と申します。今日は朝早くからどうも、ようこそおいでくださいました。で、時間になりましたので、まだ来ていらっしゃらない方もいらっしゃるようですが、始めたいと思います。で、最初にですね、ちょっと簡単に全体のご紹介をしたいと思います。はい、じゃあちょっとここからは英語でやりますね。はい。Okay, so good morning, good evening, and good afternoon. So my name is Kengo Nakajima. I'm leading a research and development division of the JCHPC and a faculty member of the Information Technology Center at the University of Tokyo. So welcome to the introduction to GPU programming models. And before going to the main part, so I will briefly describe the background. So JCHPC, Joint Center for Advanced High Performance Computing since 2013. So it's a collaboration between University of Tsukuba and University of Tokyo. From the logistic point of view, so budget of the two supercomputing centers are combined. And our purpose is promotion on computational sciences, design, procurement, and operation of large-scale systems. OakForest is the first system of the JCHPC with more than 8,000 Intel Xeon Phi night running processor. It's a peak performance at 25 petaflops. The full operation started December 2016 and retired last March. And it's one of the biggest systems in Japan, and the national flagship system, in fact, after shutdown of the K computer during 18 months. We are starting the procurement of the successor of the OFP2. Its operation starts in April 2024. So this is a history of the supercomputers of the University of Tokyo. So we are now in the mid of the fiscal year of the 2022. And recently, so we have increasing systems with GPUs. And today, we are focusing on this OFP2 and Mercury system. So JCHPC is now shifting to GPUs. It's in order to attain the maximum performance and the constraint of power consumptions. Now we are introducing two systems. So one is a very small one. It's called Wisteria Mercury. It's a small GPU cluster with 100 GPUs. Okay. And starting of the operation is next year, June. And the larger one is the OFP2, and it's a successor of the OFP. And we are expecting the 200 or larger number of the petaflops. So we have two types of the node groups. One is a group A with a combined CPU and GPU, and another one is only CPU part. Basically, so we are adopting the same GPUs for the Mercury and OFP2. And the group A and group B could have the different CPUs. And the porting codes of the more than 3,000 users of the OFP to GPU is the most critical issue. And we are now starting this. Okay. The work for porting to GPUs should begin in the fall of 2022, now at the latest, because the operation of the OFP2 starts in April 2024. It's just 18 months from now. The GPUs for both Mercury and OFP systems, they are the same, must be determined before then. So this is the history of our recent activities. So we started pre-benchmarks for selection of the target GPUs on Mercury and OFP2 this February. And we asked some GPU vendors, and so took 3 months. And 7 benchmarks in CSC written in both of the Fortran and C. And June 2022, we decided the GPUs for Mercury and OFP2, so for the NVIDIA's GPUs. Based on the performance, ease of porting, and support system, and Fortran support. And so this is a very special situation in Japan. So we have many Fortran codes, especially for the in the area of the CSE. And then now we are starting the porting, and then we are introducing the new systems. So how to port your code? So if your code is already parallelized by OpenMP plus MPI, porting to GPU is not so difficult. Sometimes you need to change data and loop structures, such as array of structure or structure of arrays, etc. And we have a variety of the programming environment: OpenACC, OpenMP, CUDA, and standard language. And we start to host online mini camps frequently from December. And you can bring your code and the members of JCHPC and the GPU vendor. So this is NVIDIA will support porting. So this is the outline of the today's lectures. And so thank you very much for the many registrations. It's over 70. And the varieties of environments for programming are available on our target GPU. So our target is NVIDIA's H100, as I mentioned before. The speaker today, Jeff Larkin from NVIDIA, will introduce some of those with code examples and performance evaluations. We hope this lecture will be helpful for you to choose appropriate programming environment on the GPU for your code. The lectures and Q&A sessions are video recorded, and it will be open to public through our homepage with this file. And you can also watch the following video. So this one is in Japanese, and so it's focusing on the OpenACC and the CUDA, but it's also very nice video. So before going to the main part, so I'd like to introduce our speaker, Jeff Larkin from NVIDIA. So he's a previous HPC application architect in NVIDIA's HPC software teams. And I'd like to highlight that this is the second part. So he's passionate about the advancement and the adoption of the parallel programming models for high performance computing. So you can understand he's one of the most appropriate persons for lectures such as today's. Okay? And he worked for Cray Supercomputing Center of the Excellence in ORNL before. Okay, so I'd like to start the lectures, and so let's welcome Jeff Larkin. Okay. So please start.
Thank you very much for the introduction, and hello everyone. I'll turn my camera on just long enough to put the face to the voice while I begin to share my screen. Okay, so I want to discuss briefly, just to set some expectations for what I hope you'll get out of this session. It is a very short session, and I'm covering a lot of topics. So I don't view this as a tutorial. Any one of these programming models I discuss could easily have a 1 or 2 or even a full day tutorial dedicated to them. But I want to give you enough information so that over the next few months, as you begin to adopt GPUs in your applications, that you have the information to help you decide what is the right approach given your goals and given your application. I'll also point out that this is not a complete survey of all possible GPU programming models. For instance, I have nothing about the Julia programming language in here, and that's one that I get asked about a lot, and it is a viable programming model, but I wanted to really focus on the ones that we support most directly in our software. I've tried to link where possible to places where you can get more information. So after I'm done talking and you've decided what approach sounds best for you, you have a link and a place to go to get started. So I'm going to start off telling you about our vision for how you should program to our platform and make sure that you understand where we're coming from and how we envision that you should approach our platform. Next, I'm going to go into some individual approaches, and I've grouped them together. Standard languages, so using C++ and Fortran without any extensions. Compiler directives like OpenACC and OpenMP, which are really popular in legacy codes, particularly in Fortran. Python, which has really emerged recently as a viable option to many HPC programmers. and is used a lot in pre and post processing. And then I'll end with CUDA C++ and CUDA Fortran. So I won't waste any time here and just go ahead and get started. So I'm going to talk about at least 8, maybe 10 different programming models. And I want to point out to you that all of them, no matter what level you're programming, a very high level or a very low level, boil down to the same thing under the hood. Your process begins execution on the CPU. You identify important parts of the calculation, important data structures, important loops. You offload those to the GPU using some parallel programming model, and then you get the results back. The best performing GPU programs are going to have a lot of green boxes here, offloading as much as possible to the GPU, and having only very little on the CPU. But it is important to keep in mind that they do work together. And it is appropriate to identify parts of your code where the GPU may be busy doing one particular calculation and the CPU can be off doing other things, maybe a smaller linear solver, or maybe handling I/O or communication. So really it's being able to program the two of them together that'll give you the best performance. And several of these programming models are really enable you to use the same programming model both on the GPU and the CPU, so you don't have to write very specific code for both. So in the back of your mind, whenever I describe these programming models, remember that your data will be moved to the GPU, and the GPU executes things called kernels. And a kernel is a function that is called by every single thread on the GPU. How that kernel is generated, it might be generated by a compiler, it might be written by hand by you, but everything kind of boils down to this model. Now, in terms of programming our platform, I want to emphasize the word platform because, as you know, we, of course, are best known for our GPUs, but we also have coming in the future, just next year, our Grace CPU, which is a very powerful ARM CPU, and we also have the interconnect. And so while historically we would focus completely on programming to the GPU, it's important now that we present to you, the programmers, a way to program all of this in a coherent manner. Now, at the bottom, I consider the foundation of our platform our accelerated libraries. You can build your applications on these libraries. We can build these further programming models on these libraries, but it all starts here. In terms of libraries, I call a core library something that creates data structures or high-level algorithms that run on the GPU. A math library does things like linear algebra, FFTs, random numbers. Communication libraries are important, and this is MPI, this is SHMEM, and we have a library called Nickel as well. And then there's some additional libraries for data analytics, AI, and most recently even this simulation of quantum circuits. So everything is built upon this this basic foundation here, which means that with every release of our software, as we improve our math libraries, if you rely on our math libraries, you're going to see that improvement. And consistently over time, as we release new versions of our libraries, you'll see the GPU that you bought, that you buy next year will be faster a year later because we will continue to improve our math libraries. Now, I'm going to talk about, at a very high level, 3 approaches that you could take to write to our platform. The one that I'm most excited about is accelerated standard programming languages. So this is, here I'm showing standard C++ with no extensions, and we can build this and run it in multi-core on the CPU or on the GPU without any code changes. And this is fully standard compliant C++. So if one day you decide you want to run it on another platform, well, you can, because it's C++ and it will run anywhere the C++ is supported. Similarly, for Fortran, I have here a do concurrent loop, which is it replaces the standard do loop with this do concurrent. It's a little more modern. It's still standard compliant, and it tells the compiler that these loop iterations can be run in any order. So these standard language approaches mean you're not porting your application to a GPU. You're writing parallel code that will run great on a CPU or on a GPU, completely unmodified. Now, the next step across is compiler directives. And compiler directives show OpenACC at the top and OpenMP at the bottom. And as Professor Nakajima said, I've worked in both of these committees and have helped with the development of both of these. Compiler directives have two nice purposes. One, if you're writing your code using a construct like do concurrent, for instance, and you need to get a little more performance, and an example of this is you write your code and it's completely parallel with do concurrent, but there's a little bit too much data traffic between the GPU and the CPU memories. You can use OpenACC to augment that and optimize those directives. So it can be used as a incremental and portable optimization to these approaches. It's also commonly used in legacy codes. And in the first part you heard, there's a lot of legacy, in particular legacy Fortran codes in the world. And frequently using compiler directives are the quickest way to get those legacy codes running on the GPU. You can go identify the important loop nests, parallelize those, and once you have everything running on the GPU very quickly, then you can evaluate, well, do I want to refactor the code maybe using these standard approaches, or do I want to further optimize the code using a CUDA approach, or maybe I'm happy with it and I want to leave it there. So compiler directives serve that dual purpose of supporting legacy codes, but also augmenting and optimizing these accelerated standard languages. Lastly, on the right is our CUDA. We have CUDA C++ and we have CUDA Fortran. And we view these as a language where we can innovate. So we design these languages along with the hardware. So when there's a new hardware feature that comes out, it's going to appear first in our CUDA languages. And then as it's adopted, we can begin to propose it to these other languages. And so it enables us to expose our hardware features quickly to our developers. Secondly, if your goal is, I know what GPU I have and I want to get the absolute best possible performance on that GPU, CUDA gives you every single knob necessary to tune and optimize it and specialize the code to the platform. So before I leave this slide, the last thing I'll point out is all of these approaches completely mix and match together. And I've seen applications that have a little bit from each of these columns plus accelerated libraries. And so you can maximize what's important to you. If productivity and portability is the most important thing to you, you would probably want to start with these accelerated standards. If maintaining a legacy code is the most important thing, you might start here in the middle with OpenACC, or if you're willing to ground up rewrite and to try to get the best possible performance, you can use a CUDA or mix all of these together. All right, so I mentioned that accelerated libraries are the foundation, and so I'll briefly mention some of those libraries. We identify the common cases that people need, and so things like the BLAS, the basic linear algebra solvers, cuSolver, which is akin to LAPACK for high-level linear solvers, cuSparse for sparse solvers, cuRAND, cuFFT. So each of these has an interface that enables you to, if you're already doing a lot of work with BLAS, if you're doing a lot of dense linear algebra, rather than going out and writing your own matrix multiply routines or things like that, you can leverage our libraries. Similarly, FFTs, if you're using FFTW, for instance, it's fairly natural to move that to cuFFT for the GPU. So each of these is available to you, and I view this as a starting point. If you can use a library, then it's basically free GPU acceleration that we've already done for you. And at a high level, our priorities for these libraries are first that they're seamless to use. And so what that means is as we introduce features into the hardware, we're going to implement those features in our libraries first. And so here's a picture of one of our tensor cores, which is optimized for small matrix multiplication routines. Well, you don't need to learn how to write code to use this low-level feature. Many of our libraries use it out of the box, and so it's seamless for you. It's important that you're able to scale up. And so if you have multiple GPUs on the node, Or if you have multiple nodes, and Professor Nakajima said you'll have at least 128 GPUs in at least 32 nodes. And so these libraries will enable you to be able to scale up to all of the GPUs on your node. Or in the case of some of our libraries, cuSolver and cuFFT in particular, you can actually scale up to full system scale without any code changes. Next, it needs to be composable. And so increasingly, we've provided support for calling our math libraries directly on the GPU, which is important. As our GPUs get bigger, we need to make it easier for you to call into these libraries. And lastly, it's a priority to us as the Grace CPU comes out that we provide the best possible ARM libraries as well. And so we are developing math libraries that are very well tuned for ARM as well. So these are our main priorities. So I encourage you to go and look into those libraries more as you look for solutions for your applications. Next, I'll talk about the standard programming languages. And I'll start with C++. C++ is a parallel language. It has been since C++ 17. We now support what's known as the C++ parallel algorithms in our compiler that enable you to write the code once and build it and run it on a CPU in parallel, or build it and offload it to the GPU. And so the data that I'll show you on the next slide will demonstrate this. And I'll point out that we are continuing to support going forward. We have features of C++ 23 that we're already previewing in our compiler, and we're already working on features for C++ 26 that are in proposal, and we're working to support even ahead of the language. So we're very active in making sure that C++ is a viable and vibrant language for HPC. So to demonstrate this, I have an application called Lulesh. This is a small C++ application that comes from Lawrence Livermore National Laboratory in the United States. Its baseline code was written with OpenMP. And so if you're familiar with OpenMP at all, this should look fairly familiar. I generate some CPU threads. I share the work of this loop to those threads. And you can even see here I have some if-defs to make sure that I can still run the code sequentially or in parallel. So this code was written by OpenMP experts at Lawrence Livermore National Lab. We took it and we rewrote it using only ISO C++. And this is the code on the right. You can see it's much smaller. It's easier to read. It will be easier to maintain long term. And it is completely ISO standard. There's nothing special here. There's nothing non-standard here, which means you can take it to any C++ compiler in any platform. And to demonstrate that, here I have data using 3 compilers. The bright green is NVIDIA's NVC++ compiler, the dark green is G++, and the dark blue is the Intel compiler. And you can see that the OpenMP code runs roughly as well across all 3 of these compilers this is a modern AMD EPYC CPU. If I play with the environment variables, I could get all of them to run at basically the same speed, but this is the default setting. Rebuilding using the same 3 compilers on the same CPU, you can see I get about a 2x performance improvement in the ISO C++ code. And on top of that, I can take that ISO C++ code with no code changes running on the GPU as well using NVC++. So this is a programming model that has no extensions to the language. It's purely C++, and it can run across here. I'm showing 3 compilers and 2 different hardware platforms. So we're really excited about the possibilities of this. And I'm happy to report that we could do very similar things in Fortran. Fortran is also a parallel language, and the 2 areas that we've really focused on are array math intrinsics, things like calling matmul, and the do concurrent loops. And so here is a simple application that was developed at Oak Ridge National Lab called Miniweather. If you look at the code on the right, it's pretty easy to understand as Fortran code. The only thing that's different from the original code is instead of having 3 do loops nested here, I have 1 do concurrent. And this tells the compiler that across all of these iterations, I'm free to parallelize that and offload it. And in terms of performance, you can see on the CPU, the do concurrent runs equally well to the OpenMP, and on the GPU, it actually runs equally well to OpenACC. So we're really excited about this possibility. And for your Fortran developers, I really hope that you will pursue this path because, again, this is a way to write code. You don't have to port to the GPU. You write the code once, and it will run on any parallel platform. So that's the standard languages, and those are I have links at the end where you can get more information about both. Next, I'll talk about compiler directives, and I know from the introduction that you have some experience with both OpenACC and OpenMP. OpenACC is our preferred of the two. It does have some semantics that make it, in our opinion, easier for you to use and also easier for the compiler to generate good code. So I would encourage you to take a look at OpenACC, but we do support OpenMP as well. The directive-based parallel programming model, we're well aware of more than 250 applications, and 3 of the top 5 HPC applications in the world use OpenACC. In terms of what it looks like, this came from a teaching code that we have. It solves the Laplace equation here, and you can see it solves this iteratively. The thing to note here is there's very little code that you need to add when parallelizing an application with OpenACC. Here I've identified this important loop nest or this other important loop nest. I've added a pragma around them, or in Fortran it would be a directive, and that's all that needs to be done. I don't need to tell the compiler how I want the loop to be run on the GPU. I simply tell it I want this to run in parallel, and it gives the compiler a lot of freedom to figure out the best way to optimize this for a CPU or for a GPU. So we've seen a lot of success, particularly in Fortran codes using OpenACC. OpenMP is an option as well. You can see here, I've taken the same code. OpenMP requires a bit more knowledge from you, the developer, because it provides a lot of different ways to write the same thing. You can place directives on each of these loops, and depending on where you put the specific directives may get very different performance. And so, in my opinion, it is more difficult in that sense that you really need to understand exactly what the compiler is going to do from those directives. We do support the loop directive, which is designed to give the compiler a lot more freedom. And so if you're going to use OpenMP, our preferred approach is for you to write this here, target teams loop. And what that does is generate a GPU kernel, but tell the compiler that it has freedom of how to optimize it. Again, I can't go into all of the different ways that this can be parallelized with OpenMP, but I'll show you here that this is the way that we believe works best. Now, briefly about Python. Python is an emerging language in HPC. A few years ago, I would not have even said anything about it. I would have said people prototype in Python and then write it in C++ or Fortran. But today we are seeing people who want to write full applications in Python and expect them to scale. And so there are several approaches that you can take in Python. One of the most widely used approaches is CuPy. CuPy implements a subset of NumPy. NumPy is probably the most widely used Python package, at least in numerical programming. And it implements a portion of that for the GPU. And so it can handle things like allocating the arrays of various data types, manipulating the arrays, and even doing linear algebra operations across them. And so here you can see this code on the right is written with NumPy. I create an array and I rearrange the array and then perform some reductions and linear algebra on it. So all of these operations are being done inside the NumPy package. And if I want to run this on the GPU using CuPy, it takes almost no change. I change from NumPy to CuPy, and now I'm able to allocate for the GPU and do these operations on the GPU. So this is probably the most common approach that I've seen people doing with GPU programming in Python, but it's not the only approach. A similar package to first package. Oh, let me get rid of my audio here real quick. So a similar project that is a little bit more ambitious is NVIDIA's cuNumeric package. What cuNumeric does is it likewise aims to implement a subset of the important subset of what's available in NumPy. But instead of just making it possible to run that on a GPU, it's actually designed so that you can distribute it to more GPUs and even up to full system scale. And so you can see down here at the bottom that there's nothing in this code that talks about parallelism. This is all written using the NumPy API. And by importing cuNumeric, we were actually able to scale it out to 1,024 GPUs. So this is a really exciting project. It's a very ambitious project. It's available online and it is currently in alpha. And so I encourage you to take a look at it and see whether it meets your needs. But I recognize that for some people, this may not be the right approach for you. One more Python approach is Numba. And Numba is an interesting approach. In many ways, it reminds me of OpenACC, but in Python. So you can see up top here, let me get my laser pointer back. You can see up top that we import numba.cuda, and then that gives us several packages or several functions that we can use to write code for the GPU. So for instance, I've written an array add function that takes A and B and adds each value together and into this output array. In order to run that on the GPU, I use this decorator here. That's what this thing is called. That says, do a just-in-time build of this function for the GPU. And then down at the bottom, when I call it, I just give a little exclamation. I say how I want to parallelize on the GPU. So this looks a little bit like CUDA here. And I pass my data in, but I haven't had to do anything special here. I'm just using NumPy, and I'm building this one function specific to the GPU. So this, I've seen a lot of people have success with this. This is a really, if you need to take a little bit more control over the code than what CuPy provides, this enables you to write GPU kernels, but in Python. So that's very nice. Finally, I'm going to talk about CUDA C++ and CUDA Fortran. Now, I would imagine many of you expected me to start with these because most people, when they think about writing for NVIDIA GPUs, they think about writing CUDA code. But as I said at the beginning, CUDA for us is a language of innovation. It's a language that you can use to specialize your code to our GPUs. But I present it last because I want you to recognize that you can use these higher level approaches and be very successful. Or if you choose to, you can use CUDA as well. So here I'm showing both C++ on the left and Fortran on the right. And so CUDA code is written in two parts. I need to write the kernel. If you recall back to the beginning, the kernel is the function that gets called on the GPU by every thread. Whereas all of those previous approaches, the compiler in some way creates a kernel for me. In CUDA, I need to explicitly write the kernel myself. And so you can see this additional keyword here, global, tells the compiler to build this for the GPU. I have to figure out for myself what piece of work each thread does. So here I'm taking these built-ins here to figure out, okay, each thread knows where it calculates into the calculation, and then I perform the actual addition here. So it's much more explicit. You as the programmer decide absolutely everything. So that's what the kernel looks like. The second part is, how do you call that kernel? And so here again on C++, you can see I need to allocate memory, and I'm going to use this CUDA malloc managed. And what that does is it allocates a single array that can be used both on the CPU and on the GPU. So how does that work? Well, when I access it first on the CPU, it's going to be, all of my data will exist in CPU memory. When I launch the kernel, the very first time I access that array from GPU space, the GPU driver way down in your OS kernel is going to migrate the data out of CPU memory and into GPU memory. So that adds some overhead the very first time, but the more code you run on the GPU, that overhead goes away. And so here, this would not be a very efficient code here because I used these arrays once in one simple kernel, and then I free them. But if I had lots of kernels here, then that cost of migration goes away. On the right, CUDA Fortran does things a little bit differently, and I have found that it's very natural as a Fortran programmer to write this code. You can see rather than calling a special function to allocate my memory, I attach an attribute to my arrays, and then I just call allocate. And then down here, I could call deallocate to free them later. And there's actually a typo here. This should just say A, B, and C. When I want to launch the kernel, I do need to tell it, I want 512 threads in each block and how many thread blocks I want. So that's what I'm calculating here. And then it launches this kernel. So, the basic parts here are allocating your memory, launching your kernel, synchronizing the device. So when I launch something to the GPU, it returns immediately to the CPU. I need to then wait for my results before moving on, and then I can free it later. And obviously here I'm not showing any of the filling of the array or the using the array later. You can be more explicit than this. This is a really nice approach when I'm starting out because I don't need to think about managing 2 copies of all of my data. It's just A, B, and C. But you can be more explicit. And this is a lot of the older CUDA examples that you would see would take this approach where first I allocate a host array, A, B, and C. And then I allocate a device array, A, B, and C. And then I need to copy my data to that. So somewhere in here, I've initialized those arrays. And then I launch my work and then I copy it back. So this is much more explicit, but it won't have those overheads the very first time I call the function of migrating the data because I've already done that automatically. CUDA Fortran, this is really, I think, very neat. So here I just changed one word up here to, instead of saying managed, I say device. And so now I have the CPU A, B, and C and the GPU A, B, and C. And again, I'd simply call allocate on them. And this could be one allocate. I did it in 2. And then instead of calling CUDA memcopy, I just say device of A equals A. And it automatically knows what that means and how to translate that. So this CUDA Fortran is at a very high level and a very natural for Fortran programmers. So this is what this code would look like. So, okay. So now I've scratched the surface on all of these programming models. And before I close and let you ask me questions, I want to tell you, well, how do you get access to these programming models? And for that, we have a product called the HPC SDK. The HPC SDK, it's not a GPU programming kit. It is an HPC programming kit that it gives you everything that you need. So it supports C++, Fortran, C, OpenACC, OpenMP, and CUDA C++ and CUDA Fortran. So all of those programming models. It gives you all the compilers you need. So NVCC is the CUDA compiler. NVC, NVC++, NVFortran are the C, C++, and Fortran compilers. And everything I talked about with standard C++ and Fortran are in these compilers. And then a whole bunch of libraries that give you what you need. So here are high-level libraries for basic algorithms or C++ standard library features, math libraries for BLAS operations, tensor operations, FFTs, random numbers. This is not the full list, but there's we provide lots and lots of libraries and the communication libraries you need. And lastly, because we recognize that you need more information as a programmer to be successful, we also include profilers and debuggers. So this is a product that we ship about 8 times a year. It's typically every odd month. So we just shipped one in September and we intend to ship one in November, plus an occasional bonus release. And it's completely free, regardless of whether you have a GPU. So you can download it for your laptop. You can run it up in a cloud instance. You can install it via SPAC. It's freely available everywhere. And importantly, it supports x86, ARM, and OpenPower. So if you build using this SDK, you can take it and run it on x86. You can take it We have examples of people running on the Graviton 3 processor from Amazon, or also the Power processors from IBM. So one SDK, once you're using our SDK, you can rely on being able to build and run on all of these ISAs. So some final thoughts. NVIDIA provides a wide range of programming models for you. Each of them is mature and ready for you to use. And many of them, in fact, are not just GPU programming models, but parallel programming models that work well with CPU and the GPU. You can mix these together to get the right balance of productivity, of portability, and of performance. And so I encourage you to dig into each of these so to get more information, because I couldn't possibly present enough information about all of them. And for that, when you receive these slides, I have linked several talks and also a variety of documentation examples that I encourage you to check out. And I will provide these slides as soon as I fix my one typo. So with that, thank you for the time, and I welcome your questions.
Okay, thank you very much. Very excellent talk. So any questions from or comments from audience? 何かご質問ありましたら、マイクロフォンをオンにしてご自由にしてください。
So can I get started? Thank you very much for the great overview. So I have seen this Rulesh performance study example several times, and I was always impressed. But at the same time, I always wonder, where do this performance difference between OpenMP and standard C++ actually come from? So in this particular example, so when you, okay, so let's first talk about the CPU thing, so not GPU. So yep. you get consistently something like 2x performance improvement between OpenMP.
Yeah. So I'm glad you asked that. And I can show you, I think there's two reasons. One part of it is I'm staying in one programming language. And so the compiler has more complete knowledge to optimize. I think that's actually only a very small part of the speed up. I think the larger part is that the OpenMP code is not as well optimized as the original authors thought. So if you look here, I have a transform reduce. And so what this does is it applies this lambda to every single element in the array, and then reduces it down to find the minimum here. And I don't know why they didn't just call min here, but that's just a minimum operation. If I look on the left, the transform corresponds to this loop, and the reduction is done way down here in another loop. And so I think there's extra overheads here where they did this part in parallel, but neglected to parallelize this reduction here. And so when this was refactored, by choosing the appropriate algorithm here, I think that is probably the largest source of the speed up. And we've seen that in other applications as well, where this one is pretty obvious, but I know of another application where this loop up top appeared in one function and the reduction appeared in another function. And so it was not obvious to them that they could call transform reduce. And so they got a speed up, but when they recognized that they could combine them into one operation, they actually got an even larger speed up. So I believe that's where the bulk of this improvement came from.
Okay, so thank you. But so in this particular example, after you recognize what you're actually doing is a reduction, you can actually introduce a reduction clause in the OpenMP 1.2.
Yeah, I believe they probably could rewrite this to do an OpenMP reduction here.
Okay,
they have not.
And the second one is about the GPU. So generally speaking, so when you compare OpenMP offloading and standard C++, so in terms of the level of abstraction, they are both are very high level. So you don't have so many performance tuning knobs available to CUDA programmers. So when you think about how you choose between standard C++ and OpenMP, so what kind of performance improvement can we expect from going from OpenMP to standard C++? So in this particular case, the reason was clear, but
so let me show you two slides for a different presentation.
Okay.
So I'm sure you're familiar with the stream benchmark. It
Mhm.
is, the maximum achievable memory bandwidth, doing copy, multiply, add, triad, and in the case of this one, they added a dot product. So this is an artificial benchmark that gives you a high water for how well you can saturate your memory bandwidth. This is the entirety of the compute code written in C++, so it's very compact. And this data comes from Simon McIntosh Smith's group at the University of Bristol. And so first I'm showing here on the CPU, you can see that comparing between OpenACC, OpenMP, and standard C++ on the CPU, the C++ is pretty competitive with the other two. There's some weird outliers, but on the whole, they're kind of similar in performance. But I think what you're really interested in is on the GPU. And on the GPU here, again, we compare OpenACC, OpenMP offloading, CUDA, and standard C++. So this is two subtly different versions of the C++, but this is what I'm showing over here is the index version. And you can see that across the board, actually, even compared to CUDA, they got very close to CUDA performance, and even in this one case, outperformed their CUDA version. So it is certainly possible to get very close to CUDA performance, even using these high-level algorithms. But there are some weaknesses to this approach. And the primary weakness right now is that every single one of these is synchronous with the CPU. So I'd launch this GPU kernel and I wait for the results. And then I launch this one and I wait for the results. And that adds a lot of overhead that won't get measured by this, but will appear in a real application. And so in reality, what we're seeing in real applications is you're somewhere, say, a 20 to 30% performance loss is what I've seen in some applications. Now, that said, we are working with the C++ committee on a new feature that's coming in C++ 26 that addresses that limitation by making it possible to launch these standard parallel algorithms asynchronously from the CPU, more like CUDA, where you would chain together the kernels. And we expect that that's going to make up this difference. And in fact, we're so confident that about this proposal that by the end of the year, we will have a version of that available for you to begin using, even though it is actually a C++ 26 feature.
Okay, thank you.
May I have a question?
Absolutely.
Can you hear me?
Yes.
Thank you. So today's talk is a very overview talk, and so I'd like to make an overview question. So that as shown in your last slide, there are so much languages already, and you introduced a new approach of the standard language C++ approach also. So I think that many of today's listeners, there's not so much professional GPU programmers. So my question is that you and some other companies already showed a bunch of the number of the languages, and perhaps a novice user of the GPU computation is very confused to which language they have to use. So I know that each language has characteristics and the performance behavior, but then how about can you give some several flowchart of the language? Application, their characteristics, or the level of the programmers to course from the ordinary C-based OpenMP plus MPI or ordinary Fortran-based OpenMP plus MPI to reach to the successful GPU computation. So I think there are maybe a couple of the flow to how to shift from the standard language to the GPU-related language according to the some relationship with language model and applications performance behavior. So if you have some kind of the chart or recommended way of the shifting to these GPU languages, it will be greatly helpful for them. How do
Sure.
you think that?
Sure, that's a wonderful question. So, if you are developing new code, a new application or new functionality in your existing code, my preference would be that you write that code using standard C++ or standard Fortran, because this is code that no matter where you run today, even if you ran that code on your phone, it's going to be running on a multi-core processor. So there's no reason to write serial code anymore. And so what you could do is start with a baseline code that is already parallel. And so it's using C++ or Fortran, if you're developing brand new code, you could start off with a code that is ready to go day one on your multi-core CPU or your GPU. If you're maintaining a legacy code, I think you're more likely to have immediate success using OpenACC because you've already identified, you already know the important loops in your code. Those loops are very well tested, they're well understood. And so all you're doing is giving the compiler additional information about your existing code in order to parallelize it. So for legacy codes, and we especially see a lot of success in Fortran in this, but in C and C++ as well, I would recommend OpenACC. OpenMP is fine too, but as I said, we actually believe that you will have a better experience with OpenACC. And then the last part of the flowchart would be, new codes, I would say standard languages. Existing codes, I think compiler directives. And then lastly is when you have the bulk of your code running on the GPU, and then you identify, okay, this is the most performance critical function in my code, the most performance critical subroutine. Then look at writing that one part or that small number of parts in CUDA C++ or CUDA Fortran. And the reason I say that is with CUDA C++, CUDA Fortran, you have to fundamentally rewrite a lot of your code. You're going to have two versions. You have a CPU subroutine and a GPU subroutine. So it takes more time. You will probably get the best performance overall, but more time. So by choosing to use these other approaches first, you get more of the code running on the GPU, which Amdahl's law would say is more valuable than getting an individual function running very fast. So in my opinion, CUDA C++, CUDA Fortran, that's the last step in this flowchart. Now, I did kind of neglect libraries, and I think libraries are perhaps kind of the priority zero. If 80% of my runtime is doing large matrix solves, you can right away, and possibly with no code changes, see a speed up on the GPU using our math library. So you look for those opportunities first. But then, as I said, for new code, I would suggest the ISO languages, C++ or Fortran. For legacy codes, I would suggest OpenACC. And then as a last optimization step, I would suggest CUDA, either C++ or Fortran.
Okay, thank you very much. So anyway, this situation nowadays is called as a language explosion. So that I think that always I'm asked by the application users. I'm a system guy, but if we rewrite our code in some specific languages, so how that language and how that the supporting system can survive. So the users want to survive with their code for 10 to 20 years, so that we have to be something responsible for the code writing support system and also the language and the devices. So that I think that then you have a more specific, not just an overlooking, but the specific example and the writing, or also how long time it should be taken to rewrite their code, or such an real evidence is support it. I think it's a very good help for these users. Thank you very much.
Yep, absolutely. And you point out, HPC codes need to survive 10, 20 years, maybe more. I didn't get to show it here, but we've worked in games, which is a computational chemistry application that's been around for more than 40 years. And they've gone through and they have OpenMP in the code, but they've recently added Duke Concurrent, and they're actually getting better performance out of Duke Concurrent. But there's a lot of code. You can't rewrite a 40-year-old code overnight. And so one of the reasons I really emphasize the ISO languages is there is no better track record for a language surviving than ISO C++ and ISO Fortran. In terms of compiler directives, OpenACC is 11 years old. OpenMP as a specification is older than that, and in terms of the offloading is about 8 or 9 years old for offloading. So these have already survived a long time, and I fully believe they will continue to survive. I can't imagine a day when ISO C++ completely goes away.
Okay, thank you.
So any other questions or comments? Yeah, I have a related questions. And most of the legacy codes are written in OpenMP. And I think most of the users want to run the same code or similar code on both of the CPU and GPU. But you recommend the OpenACC, not OpenMP, for the such kind of the legacy users. And do you have any plan to improve some interface or performance of the OpenMP?
So what I'm showing here is the improvement OpenMP. So in the OpenMP that most people have learned, in this case would type OMP parallel 4. And that's very specific. It says spawn some number of CPU threads and divide this outer loop across those threads and run this inner loop sequentially. And so right away, I'm limited in not given enough parallelism to saturate something like a GPU. So I need a different version to run on the GPU. And so instead of typing OMP parallel 4, I might type OMP target teams distribute parallel 4 SIMD. So it's a lot of typing, and it's fundamentally different. I worked very hard in the OpenMP committee along with several other people from other vendors as well. Intel, AMD, IBM were all involved in this, the national labs, for this directive called Loop. And Loop was designed to give the compiler similar freedom to what it has in OpenACC. I know when we presented this idea to Tim Matson, who works for Intel and has taught OpenMP for many years, his excitement from it was, well, now there's a way that I could tell people to write one thing rather than saying, well, first you learn parallel 4 and then you learn target teams distribute parallel 4. And so what I'm showing here is what we believe is the most generic you can get. So target says you would offload it to the GPU or not. You can actually say if n is greater than 1,000, offloaded to the GPU. Teams generates coarse-grained parallelism, so that it could be CPU threads, it could be NUMO domains, it could be GPU thread blocks, but it generates parallelism. And then loop just tells the compiler, I promise to you these next 2 loops are safe for you to parallelize however you want. And so this really is the most generic. Some people have actually taken this a step further and say OMP target loop, and that's fine as well. That basically gives the compiler complete freedom to figure out exactly how much parallelism to launch and how to parallelize it. So if you're going to do OpenMP, using this loop directive is your best opportunity at portability between CPU and GPU. Without that, you will absolutely have to have an if-def in your code that says on the CPU do this and on the GPU do this other thing, and on a FPGA go do this other thing. So loop is a way to write generic code. In talking to users, I've heard from several users that this is working very well for them, and even have had one say that they would not have been able to use OpenMP without it. So if you're going to choose OpenMP, my encouragement is to use Loop rather than the traditional OMP Parallel 4, which is very limited in its capabilities.
Okay, thank you very much. And it's almost time. And any quick question?
Can I ask a question?
Okay, go ahead.
I have some related question. So the language is very important, and I thank you very much for the talk. So how about the performance portability for because of the we need to transport some kind of code to the GPU code, and also keep it works properly, and maybe keep it scalable. So how do you think about some of the performance portability for the future generation and make it minimize maintain costs and keep it scalable?
Sure. So first, I would say that in terms of your data structures, the same sort of optimizations you would do to your data structure to make it run well on a GPU, you will need in order to run well on a SIMD CPU. So whether it's ARM scalable vector extensions or AVX extensions on x86, you need to be have a data structure that will support the vectorization there. And if you can vectorize on the CPU, you can absolutely perform well on the GPU. So then the next step then is exposing them. So one challenge is, and I think OpenMP is a good example where the challenge is. In OpenMP, I might write Pragma OMP SIMD on this loop to say I want this to be SIMD vectorized, and then parallelize the outer loop. And so the challenge becomes, well, on a GPU, I want to use all of these loops to get as much parallelism as possible for this big GPU. And on the CPU, I might actually want instead to make this a vector loop and that a CPU threaded loop. So going back to, I guess, my last comment or answer to the last question, writing something like Teams Loop in OpenMP, in my opinion, is the better option because it does enable both. On some of these other approaches, I could show you, with Fortran here, the only code change between the CPU and the GPU, there's no code change. What I've done here is I'm exposing all of this parallelism, and I'm telling the compiler, you know best how to parallelize this for a CPU. Figure out, what's the best way to do it. And I think it vectorizes this I loop and it threads over these other loops. But on a GPU, you also know best, and so it will exploit all this parallelism. So to write portable code between the CPU and the GPU, you need to expose as much parallelism as possible and do it in a way that gives the compiler the freedom to choose how to optimize it for a CPU versus how to optimize it for a GPU. But in both cases, I actually believe the data structures should be very similar. You want to access stride 1 on the innermost loop here in Fortran to make sure that you can both vectorize on the CPU and thread nicely on the GPU.
Thank you very much.
Thank you.
Okay, thank you very much. So it's time. And so thanks again for Jeff for the very interesting and very important talk for us. Okay, so let's close.
Thank you very much, and
this,
I'll send the slides later.
Okay, thank you very much. Okay, so let's close this lecture. So thank you very much again.